Welcome to this short video lecture. My name is Vincent Nando. I teach mathematics at the School of Engineering. So in this small video lecture, we are going to discuss on how to solve integral differential equation using Laplace transforms. So this is the problem. We expected to solve the integral differential equation given by dy dt equals to 1 minus the integral from 0 to t y of t minus v e raised to power minus 2v dv. And then the initial condition is y at 0 is given by 1. So this is a problem that tests on application of Laplace transforms. Laplace transform and inverse Laplace transform. To solve a problem with the help of convolution theorem. So before we solve the problem, so I'll briefly state what we mean by convolution. I'll define that one. So convolution of two functions. So convolution of two functions, if f of t and g of t are piecewise continuous functions, on the interval 0 to infinity, then the convolution of f and g is denoted by f star g and is given by, defined by this integral, that f star g, or simply convolution of f and g, is the integral from 0 to t f of t minus v multiplied by g of v dv. So this is the convolution. And then you can see clearly that the way this question has been structured, the limits 0 to t, so y t minus v, and then this is our g of the g function. And then also what will help us also to solve that one is what we call the convolution theorem. So it will be very useful to help us solve this convolution theorem, which brings in the aspect of Laplace transform and inverse Laplace transform. So if still, if f of t and g of t are piecewise continuous functions, on the interval 0 to infinity, as just we have said in the case of the convolution, and are of exponent or exponential order alpha, and if we set the Laplace transform of the function f to be given by capital F of s, and the Laplace transform of the function g of t to be given by capital G of s, then the Laplace transform of the convolution of f and g is the same as the product of the Laplace transform of these two functions. Or is the same thing as saying the inverse Laplace transform of capital F of S, which is the Laplace transform of this function f of t, the product with g of s, then is the same as the convolution of f and g. So this is the this theorem, and the definition of the convolution is the one that is going to make us reduce the problem into a much easier problem to be solved. So we're back to business, to the question. So we have been asked to evaluate the value of this integral, 1 minus integral from 0 to t y t minus v, and then e raised to power minus 2v dv, and then the initial condition was y at 0 is given by 1. So if you check clearly this one here, what we have at this point here, if you relate to the definition of convolution, you should clearly see that this is the same as y of t convoluted with e raised to power minus 2t. Just by knowing that f star g or convolution of f and g is given by integral from 0 to t f of t minus v, and then g of v dv. So remember, these f and g are functions of t. So if you relate this definition with what we have in this integral here, so this is what we have. So all this part is the same as the convolution of y of t with this function e raised to power minus 2t. So which tells us that the equation we have is the same thing as y prime of t equals to 1 minus y of t convoluted with e raised to power minus 2t. So after rewriting the integral differential equation in this form, we are going now to make use of the convolution theorem on the Laplace transforms to be able to get the value of y of t. So we let capital Y of s to be the Laplace transform of the function y of t. So we know that will be a function of s, and therefore taking the Laplace transform so let's call this one equation 1 on both sides of 1, we get, so this is what we do. So Laplace, so taking Laplace transform on both sides of 1, and also using convolution theorem and using convolution theorem, we have, so this is what I mean. So let me just first step, let me supply the Laplace transform on each of these two. This is a function of s equals to Laplace transform of 1 minus Laplace transform. Remember, this is a function of s, Laplace transform of the convolution of y and this function e raised to power minus 2t. So this part is where we are going to use convolution theorem, but this one, Laplace transform of y, we know that is 1 over s. And then the definition of the Laplace transform of first derivative of y is given by s capital Y of s, and then minus y naught, but the initial minus the value of y at t equals to 0, which is given by 1. We have 1 over s, and then using convolution theorem on this one, we'll have capital Y of s, and then Laplace transform of this one is given by 1 over s plus 2. So this is the Laplace transform of this y of t, and then this is the Laplace transform of this function e raised to power minus 2t. So then the next thing now, just now to rearrange terms with capital Y and then s, and then get the inverse Laplace transform. So this you can say s capital Y of s. So bring this one to the left. So we'll have plus 1 over s plus 2 capital Y of s equals to 1 over s plus 1. And then this, you can say this is s plus 2, and then s plus 2, s into s plus 2, and then plus this one is just 1, and then capital Y of s equals to LCM here is s, so 1 plus s. So that's what we have, or s plus 1. And then this coefficient of capital Y will have s squared plus 2s plus 1 divided by s plus 2, and then capital Y of s equals to s plus 1 over s. And then, so what we do now, we make capital Y of s the subject. So capital Y of s will be given by s plus 1 over s times the reciprocal of this one, s plus 2 divided by s squared plus 2s plus 1. So this is the same thing as saying s plus 1 into s plus 2 divided by s into s squared plus 2s plus 1. So this would be a y of s, which is s plus 1, s plus 2, and then s. But then this one, these are quadratic expressions. So product is 1, sum is 2. So numbers 1, 1. So which means we have s squared plus s plus s plus 1. So common here is s into s plus 1. Common here is 1 into s plus 1. So that we have s plus 1 times s plus 1, or simply s plus 1 squared. So this can be written as s plus 1 times another s plus 1. And you can see clearly that by writing that, this will cancel out. So this will cancel this one, so that we have s plus 2 over s into s plus 1. And then this one here, you use partial fraction. So we'll have capital Y of s is given by s plus 2 over s into s plus 1. And then we split this one using partial fractions as a over s, and then plus b over s plus 1. So that right hand side will have s plus 2 over s into s plus 1 equals to s into s plus 1, a into s plus 1 plus bs. And then, so this tells us that, so remember this still y of s, tells us that s plus 2 must be equivalent to a into s plus 1, and then plus bs. So when you set s to be 0, then this one left hand side will give us 2 equals to a. So therefore the value of a is 2. And when we set s to be -1, then we have 1 equals to negative b, so telling us that b equals to -1. So therefore, capital Y of s is a, which is 2 over s, and then minus 1 over s plus 1. And then therefore, to get y of t, so let's call this one equation 2, we apply inverse Laplace transform on both sides. On both sides of 2, i.e. this what I mean. So you say inverse Laplace transform of capital Y of s, which is a function of t, the same as inverse Laplace transform of 2 over s minus inverse Laplace transform of 1 over s plus 1. And actually this you can factor out to, and you know that the inverse Laplace transform of 1 over s is t is 1. So this is the same as 2 inverse Laplace transform of 1 over s, and then minus, this actually is a standard one, 1 over s plus 1, whose solution will give us y of t to be, this one is 1, so 1 times 2 is 2, minus this one is exponent e raised power minus t. So therefore, this is the final solution. So therefore, in this question, we have seen that we have been able to solve the integral differential equation by use of the definition of the convolution theorem and the inverse and Laplace transforms. So that is how we were supposed to solve that problem. So thank you, and have a good day.